Welcome to the first lesson on section 6.4. The topic is called separation of variables. Now, even though you're learning this topic at home, I don't want you to think that means it's not an important topic. This is actually a very important topic. It's likely to show up in the multiple choice on the AP exam, as well as the open-ended on the AP exam. So it's likely to show up more than once. The reason I've selected this topic to send you home to learn is because it's one of the ones that I would have the easiest time developing lessons that you could do on your own. For some other topics, it really need to be in class so we can have discussions and ask questions. So we'll go ahead and get started with our first example. For example 1, I do have the, if you would like to skip writing this, I do have it already worked out and posted in Classroom for you. So for our first example is we're going to solve a differential equation. Anytime you're given a derivative, that's called, in an equation, that's called a differential equation. So what we want to do here is we want to solve for just, we want to find the antiderivative essentially. But what's different about this one is that we have x's and y's in the derivative. So when we have x's and y's in the derivative, let me rewrite this. When we have x's and y's, it's not so straightforward. We can't just find the antiderivative. We can't just use substitution. So what we do is we use this new technique called the separation of variables. And here's how that works. My first step is to move dx to the other side. So I'm going to treat these as two separate quantities. And what I'm going to do is move dx to the other side, kind of like I'm multiplying both sides by dx. And then what I want to do is I want to get all the expressions that have y in them on the side with the dy, and all the expressions that have x with them on the side with the dx. So what that means for this problem is just move the y over. Since we're dividing by y, we can multiply both sides by y. And now what we have is we have all the terms with y on the side with dy and all the terms with x on the side with dx. Okay, so that's why it's called separation of variables. So we're going to separate, we're going to move the x's to the dx side, and we're going to move the y's to the dy side. And by the way, when you go to write this, you technically could write dy times y instead of y times dy, but usually we like the dy on the end. And similarly for the dx, I prefer the 2x in front of the dx. Technically this would be equivalent, but I think you'll find you like the dx on the end instead. Our next step, I'm going to rewrite to show the next step, is to now integrate both sides. Because the overall goal here is to find the antiderivative. So what we're going to do is we're going to integrate both sides using the indefinite integral. And the antiderivative of y, if the variable is y, we're just going to reverse the power rule. So we're going to add 1 and divide by the new exponent. And then since we're doing an indefinite integral, we need a constant. So I'm going to put a plus c there. And then on the right-hand side, we're going to undo this by finding the antiderivative here. And what we're going to end up with is just x squared, because when we increase that exponent by 1, it's going to become 2, and we divide by 2, we get a 1 here. Now, we also need to put a plus c on this side technically. So I'm going to tell you a little extra info here, and then I'll give you the shortcut in a moment. Now, technically, you shouldn't be using, technically you should have a plus c for this antiderivative and a plus c for this antiderivative because there's an unknown constant, unknown constant. You shouldn't use the same variable for both. So you could call this one c, you could call this one d, or you can introduce subscripts that makes them different. So this is the unknown constant for this antiderivative. This is the unknown constant for the antiderivative. But what we usually do is we usually skip this step. And what we usually do is we just put one unknown constant over here on the right-hand side. And the reason we're allowed to do that is because this is some unknown number and this is some unknown number. So after this step, if I wanted to, could I like move the c sub 1 over here? Sure. So if I were to move the c sub 1 over there, what you would have is you would have this expression, and these two together make some unknown constant. So instead of using two different variables, two different letters with different subscripts, what we can do is just replace that with just a plus c. So just to show you technically what's happening here is we are finding the antiderivative. We have an unknown constant. Finding the antiderivative, have an unknown constant. But we tend to skip this step and just throw a single plus c over there on the right-hand side. And there's no need to solve for y unless you're asked to. And sometimes you'll be asked to. We'll see examples where we're asked to do that. So there's no need to solve for y unless you're asked to do so. And we can check our answers by finding the derivative. If we find the derivative of this with respect to x, we should get this right here. So I'm going to go ahead and check, and it's up to you if you want to do the checks as you do your problem and practice sets, or if you want to, check some of them, all of them. Is really up to you. So in order to find the derivative with respect to x of both sides, the right-hand side is going to be a piece of cake. So this is going to be 2x with the power rule. The derivative constant is 0, so it's just 2x over there. The left-hand side is going to require implicit differentiation. So what I'm going to do is slide the 1/2 out front because that's a constant multiple, and then just find the derivative with respect to x of y squared. Now, since y is a function of x and the variable here is x, we need to use implicit differentiation. So that's where we treat this as a function of x, and we find the derivative of y squared, which is 2y to the first. And then it's really the chain rule where we multiply by the derivative of the inner function, and the inner function in this case is y. So it's a little while since we saw implicit differentiation, but that's the one where we would put the dy dx. Anytime we find the derivative of y with respect to x, we got to throw a dy dx on there because we got to use the chain rule. And then if you look at where we're almost back to where we started. We can get those to match if we solve for dy dx by dividing y to the other side. And sure enough, that matches what we started with. So when you go to check, if you want to check these, you have to use implicit differentiation. And that's really what you're undoing when you're using separation of variables. So the topic separation of variables, it's used to undo or reverse implicit differentiation. And there's our first example. That's the only one that I wrote out for you and attached in Classroom. For all the rest, if you'd like to take notes, you'll have to do that yourself. If you choose not to take notes, that's up to you. You can always access this video again later if you want. My next example is going to be dy dx equals 2y. So I said in the first one that we use this when we have x's and y's in our derivative. Another time we use it is when we have just y. So if we have a dy dx, a derivative of y with respect to x, but there's no x's over here and just y's, then we're also going to use what's called separation of variables. That's the name of the topic. So following the same process as last time, my first step is to move dx to the other side. Oops. Let me get my white out. So I'm going to have dy on the left-hand side. I have 2y dx on the right-hand side. And then what I want to do is I want to get anything that involves a y to the left-hand side and anything that involves an x to the right-hand side. So what I'm going to do is just slide this y over here. And when I divide by y, it's going to end up as 1 over y times dy equals 2 dx. So just to show that for anyone who has a question about the algebra, what I'm doing here is writing it wrong, so I have to fix that. Okay, so what I'm doing here is I'm dividing this side by y and dividing this side by y. And then over here, this format's going to be difficult to work with, so I like to rewrite it as 1 over y dy. And you'll get used to that in the process. Another question you might have right away is, what about the 2? How did I know to leave it over here? I didn't. It works either way. I like to, as opposed to, like, you could do this same process. You could move the 2y. I misspoke. You could move the 2y. If you wanted to move the 2y, you would divide this side by 2y and have just dx. This side would give you 1 over 2y dy. So you can work with this or with this one here. You're going to get the same answer in the end, but personally, I'd rather have a coefficient of 2 instead of a 2 in the denominator. So that's why my instinct here was, let me just move the y over and leave the 2 up here. I'd rather not work with a fraction for the 2 if I can avoid it. All right, so we moved the dx over. I got all the y's on the dy side. There's no x's, but they would go on the dx side if I had them. And now I'm going to find the antiderivative or integrate both sides. So the antiderivative of this side, since it's 1 over y and the variable is y, that's that special case where we don't reverse the power rule. It's the natural log of the absolute value of y. I'm going to skip writing the plus a constant because as we discussed before, I can just throw that on this side instead, just once. And the antiderivative of 2 with respect to the variable x is going to be 2x. Since that's a constant, it becomes linear when you find the antiderivative. And if you're not sure about that, you can check it by finding the derivative. The derivative of 2x is 2. So here's where we are. And that's our answer. If you wanted to check it, you could use implicit differentiation to find the derivative. You'll get back to here. And if you were to do the differentiation over here, you would end up with an equivalent answer to what you have shown here. And the next one I have for you is number 3. Number 3 is just to show you, you actually can use this. I don't think you'll do this, so it's up to you if you want to write this one down. This right here, dy dx equals x minus 3, is a differential equation. Anytime you have a derivative involved in an equation, it's a differential equation. But this one here, you actually could just solve this one real quick because you have the derivative. So you have like essentially of y prime equals x minus 3. If you want to solve for y, you're just going to reverse the power rule and throw your plus c on there. So this one, you know the antiderivative because it's just x. But technically, this process still works. And I just want to show you that. So like if you're in the zone of doing separation of variables and you get something where you actually just know the antiderivative, just find the antiderivative. But if by accident you're in the zone and you're doing all the separation of variables, it still works. Slide the dx to the other side. You really want to put the x minus 3 in parentheses here to remind yourself that's an entire quantity. And then when you integrate both sides, the antiderivative of dy is just y. If you don't see that, then you can always put a 1 in there. The antiderivative of 1 would be y, because if you find the derivative to check it, the derivative of y is just the 1, if the variable is y. And then over here, we want to reverse the power rule, because we have x minus 3 in the variable's x. So it's going to be x squared, and then 1/2 out front. And then we'll have minus 3x, and then don't forget the plus c for a constant. So the purpose of number 3 is to show you that it actually still works. You can still do separation of variables, even if your derivative is only in terms of x. It's just more work than necessary. It's probably easier just to find the antiderivative. And then I have one more example. This one is up to you if you want to watch it. So this one's going to be separation of variables that also involves u substitution. So if you want to go try the practice set and that goes well, then you could probably skip watching this one. But if it's up your call. So you can always try the practice set and come back to this video if you like. So for number 4, this one's really complicated. This definitely calls for separation of variables because we have our derivative where y is a function, x is a variable, and we have x's and y's all over the place. So what we need to do first is move the dx to the other side. This is all one term. It's all multiplication in between. And then I want to get everything with an x I want to leave on the dx side. Everything with a y I want to move over. So what I'm going to do is I'm going to move this whole piece by dividing it to the other side because everything here is attached by multiplication. So when I divide that all to the other side, it's going to all end up in the denominator. And then we'll have a dy on the side there. Okay. And again, for anyone who wants to see the algebra there, if you're like, whoa, how'd you end up with that fraction? Oops, forgot the square root. Because what I'm doing is I'm dividing by this entire quantity, these two factors on both sides. So on the right-hand side, they reduce out, leaving me with x dx. And then instead of leaving it in this form where I have dy in like a numerator, I'm going to move the dy to the side, keep that denominator, and then you can't leave a blank space in the fraction, so I put a 1 to hold the spot. So that's how I got to here. All right, now when we go to integrate both sides, and when you're doing your work, you feel free to put the integration symbol right there. I'm keeping it as a separate step just so that you can look back later. If you're taking notes, you can look back later and understand the process we did. Okay, but when you're doing your homework, feel free to drop the integral right in there. So the right-hand side is going to be quick because you're just going to reverse the power rule. So it's 1/2 x squared. I'll throw the plus c on that side. The left-hand side is going to be more complicated because in order to find this antiderivative, we're going to have to do u sub. So let me just work on this here. What we need to do is we need to find, by the way, because it's the only other technique we know. Either we find the antiderivative right off or we do separation of variables, which we're in the middle of. Otherwise, it must be a composition and we're going to do u sub. So what we want to do is look for a composition. I see inside of cosine I have a square root of y. So I'm going to let u equal the square root of y. And for u sub, we find the derivative with respect to the variable. The variable on this side is y. So I'm finding du dy. That's going to be 1/2 y to the negative 1/2. For u sub, we move the dy to the other side. And then I'm going to clean it up because I'm going to try to match something that's in here. So I'm going to have 1/2. I'm going to make this 1 over square root of y because I see a square root of y in the denominator. And then my next step is to try to get this in the same format as this. So I know I'm going to be replacing this with u, and I see that I have 1 over square root of y dy, but the 2 is not involved. So for u substitution, what we learned is we're going to move the 2 to the other side. That's the end of the school day when I'm recording here. So we're moving the 2 to the other side. All right, so what I'm going to do is just I'm going to split up the work here just so we can see it. So if we want to find the antiderivative of this, I'm going to split that up. I have 1 over cosine squared square root of y times 1 over square root of y dy. So this can be replaced with du, and this can be replaced with u. So now I'm going to have 1 over cosine squared u times this gets replaced with 2 du. And I'm just working on the left-hand side. I know it's made its way across the page, but I'm just working on this still. And then I'm going to bring the constant multiple out front. And I don't know the antiderivative of cosine squared. So I'm going to sneak in a little trig here for you. I wouldn't do this to you on a test or quiz, but and I don't think you'll see it on a AP exam, but I guess you could. This is a reciprocal identity from pre-calc. So we have a reciprocal identity that says secant is equal to 1 over cosine because they're reciprocals. So if you have 1 over cosine squared, that's secant squared. So what we can do is make this secant squared, and the reason that's good news is because we know the antiderivative of secant squared is tangent, and then usually we'd put our plus c. I'll throw that in now. I technically should probably put a subscript because I already used c up here. So I have 2 tangent u plus c, and then our grand finale when we're doing u sub is usually to get x involved again, but this time it's u. So we don't want u in our answer here. I want to replace that with square root of y. All right, and then again, I have that constant. So here's where we're at. What we want to do next is now that we have found the antiderivative, I can't even fit the whole thing on one screen here. Now that we found the antiderivative of this by using u sub, we're going to put that back in. Okay, so when we did all this work, we ended up with 2 times the tangent of the square root of y. I'll skip the plus c because I'm going to go ahead and put it on this side. All right, so the antiderivative of the x was 1/2 x squared plus c. The antiderivative of the left-hand side after all that u substitution was this. And if we piece that all together, what we get is 2 times the tangent of square root of y is equal to 1/2 x squared plus c. And if you want to check it, once again, it's implicit differentiation. So if you go to check this, my ... there is just to show the work I skipped there, because all the work's underneath, of course. So if you go to check this, if you find the derivative of this with respect to x, you should match this right here. So I'm going to go ahead and check it. If you don't want to watch this part, you don't need to. You can continue on to the problem set. You can always come back to this if you decide you want to watch it. I'm going to do the right-hand side first since it's quick. This is going to end up being x because when you swing the 2 around, power rule, you're going to get 2 over 2 is 1 and x to the first. The derivative of the constant is c. And then on the left-hand side, we're going to review our implicit differentiation. We're finding the derivative with respect to x, but y is a function of x. So constant multiple hangs out front. Derivative of the outer function is secant squared. You keep the inner function the same. And then you have to multiply by the derivative of the inner function. So what we're going to have for the derivative of the inner function is we're going to have 1/2 times y to the negative 1/2, because remember square root of y is y to the 1/2. And then, so this is a double link, because you have the chain rule here, essentially. That's what implicit is. And then this is a function, this is a function of y here. So we have to multiply by the derivative of the inner function, which is dy dx. So if you look at this giant mess, if we go to solve for dy dx, everything here is attached by multiplication. So that means you can move everything over at once if you want by dividing it. So I have x over 2 times secant squared square root of y. and I have a 1/2 down there. Ooh, I can reduce those out. Okay. And then I have y to the negative 1/2. And then, yes, this is correct. I'm looking at this thinking, uh-oh, why is the y in the denominator? Because that's a negative exponent. So now I have x over secant squared root of y times y y to the negative 1/2. I'm going to go ahead and move that up because that's y to the negative 1/2. So I'm going to move that up and make the exponent positive. And now I have x. Let me split this up so you can see the check here. I would just leave this in this format, to be honest, but we're trying to match the original. The original looks like this. So I want the x up top, I want the square root of y up top, and then I want a cosine squared. So once again, sneaking in a little bit of trig here, 1 over secant squared is going to be cosine squared, keeping the inside function the same. And then you have times x, and then you have times the square root of y, and sure enough, that matches what we started with. The factors are in a different order, but it does match. All right, so that's the end of the examples for the first video. You can continue on to task 2 now.